Welcome! In this lecture, we will be talking about boundedness. The notion of boundedness is very similar to maximum and minimum, but there are some key conceptual differences. Let us get started. Given a set S, we say that a number x is an upper bound for S if x is at least as large as any element of S. A set is bounded above if it has an upper bound. Similarly, a number x is a lower bound for S if x is no bigger than any element of S, and a set is bounded below if it has a lower bound. We can add the modifier strict to any of these concepts if we replace less than or equal to by less than, and so on. Finally, without the modifiers above or below, a set is bounded if it is both bounded above and bounded below. Here are some immediate consequences of the definition. First, if the set S has a maximum max S, then max S is an upper bound for S. Second, if X is an upper bound for S and Y is bigger than X, then Y is also an upper bound for S. This follows from the transitivity of the ordering. Similar statements can be made about min. Notice that unlike max and min, we immediately see that upper and lower bounds are not unique. The main conceptual difference between maximum and upper bounds is that maximum is intrinsic and upper bounds are extrinsic. When talking about the maximum and minimum of a set S, we only consider elements in the set S. When talking about upper bounds and lower bounds, we allow elements that are not in S. The difference is mainly in understanding what you need to show in order to show that S doesn't have a maximum or doesn't have an upper bound. To show that S doesn't have a maximum, you just need to show, given any element in S, there is another bigger element in S. To show that S doesn't have an upper bound, you need to show more. You need to show that given any number x, which may or may not be in S, there is another bigger element that is in S. When we allow the arbitrary element x to be any real number, to actually prove that there is something in S that is bigger could be a bit tricky, sometimes requiring the use of the Archimedean property for real numbers, which we haven't studied yet. We will postpone such examples and proofs until a bit later. For the examples of this lecture, we will limit ourselves in only thinking about boundedness and unboundedness within the rationals. So S is a subset of the rational numbers, and X is a rational number. Finite sets. Since every finite set has a max and a min, and we already discussed that maxima and minima are upper and lower bounds respectively, this means any finite set is both bounded above and below, and hence bounded. Back to the standard sets. Since n has 1 as a minimum, it has a lower bound. N is not bounded above. Z is neither bounded below nor above. Let's give a proof that Z is not bounded above to illustrate the method. First, we let Q in big Q be arbitrary. Remember, we're restricted to only thinking about rational numbers for this lecture. To prove that Z is not bounded above, we need to show that regardless of what Q is, there must be some element of Z that is more than Q. We split into three cases. Q is either negative, positive, or zero. When Q is negative, it is less than 0. Since 0 is in Z, we have found an element in Z that is bigger than Q, showing that Q cannot be a lower bound. Upper bound. When Q is 0, it is less than 1, which is in Z. And again, we have found an element in Z that is bigger than Q. Finally, when Q is positive, we will apply the Archimedean property to the pair of positive rational numbers Q and 1. This implies there is a natural number n, such that n times 1, which is equal to n, is more than Q. So again, we have found an element in Z that is bigger than Q. Finally, let's take a quick look at the set of all rational numbers strictly less than 1. In the last lecture, we showed that this set does not have a maximum. However, it is clear from the definition that every element of S is no more than 1, which means that 1 is an upper bound, and so the set is bounded above. This example illustrates an important point, that while maxima of sets are automatically upper bounds, sets can have upper bound without having maxima. We say that the property of having an upper bound is a weaker property than having a maximum because the latter implies the former, but the former does not imply the latter. Before we move on in the next few lectures about completeness, I want to talk a little bit about a related issue. In this lecture, we have pretended that all numbers are rational and forgot about the existence of irrational real numbers. Working under this assumption, when proving a set is bounded, we have to make sure to use only rational numbers, meaning that the upper and lower bounds that we find need to be rational numbers. To illustrate, we give an example. Consider the set of rational numbers whose square is less than 3. We are asked to prove that it is bounded. Naively, we want to follow the procedure in the last example, where we showed that all rational numbers less than 1 consist a set bounded above. There, we just use the number 1 as the upper bound. Here, however, the analog statement is that elements of Q and S are bounded above by square root of 3. However, root 3 is irrational and so cannot take the place of an upper bound in the context of rational numbers. What we will do is to find actual rational numbers as upper and lower bounds. In the proof on this slide, we establish plus and minus 2 as upper and lower bounds of S. The basic argument is one of contradiction. We suppose that Q is not less than 2, or not greater than minus 2. This implies that Q squared is necessarily greater than 4, and hence greater than 3, showing that such a Q cannot belong to S. And hence, elements of S must be bounded between minus 2 and 2. We conclude this lecture here. See you next time.